Okay, so in this video, we will derive the statistic for a test of independence. Now, the question will actually be very simple. Given two variables, are they independent or dependent? An example of this would be consider asking people for their favorite color. So you would have one variable would be the favorite color. So you could have, blue, red, green, and so forth. And then you could divide people up into, say, male versus female. So then you could ask, is the gender of a person and the favorite color of a person dependent or independent? So here's how we will proceed. As always, we have to state our two hypotheses, H0 and H1. H0 will always be the statement that the variables are independent. And of course, H1 will be the opposite. And you can either say the variables are not independent or the variables are dependent. Same thing. So I'll just go with the variables here are not independent. Okay. The first question is, how do we arrange data? Well, we have variable 1, variable 2, and they will be broken down into categories, right? If we say gender, this is our first variable, it would be male and female, so two categories. And if we say favorite color, then we would have more than two categories. We'd have blue, green, yellow, purple, pink, and so on. So we will arrange the data in a contingency table. So you can imagine variable number 1 and then variable number 2. And we arrange the observations in a table. Let's just assume that right now we are looking at gender and favorite color. So the first variable being gender, there would be two categories. There would be male and female. And then variable 2 would be the favorite color. And then we would have, this would be maybe blue, then green, then yellow, and so forth. And then we'd have more than just two categories. So the first two variables that we will label are the number of rows of our matrix, the number of categories of variable 2, and the number of columns of our matrix, the number of categories of variable 1. The number of rows we will label m. So this is the number of rows of our table, the number of categories of variable 2, and we will use lowercase n for the number of categories of variable 1, so the number of columns of our table. And for each cell of our table, we will have a given number. Suppose we sample a given number of people. Maybe if this were blue, maybe we'd have 20 people that were male and picked blue as their favorite color. Suppose this was red, and we look at this cell, maybe we'd have 30 people that were female and picked red as their favorite color. Since we use lowercase m for the number of rows and lowercase n for the number of columns of our table, we will use now uppercase N for our sample size. Suppose we sampled a total of 200 people, then that would be our uppercase N. So this would be our sample size. Okay, so then the question is, once we have collected our sample and arranged the data in our table, how do we then proceed to decide whether or not the variables are independent or dependent? We need a statistic. The first thing is, and you'll see that we will end up using the chi-square random variable. The first question will be, well, how many degrees of freedom will our random variable have? And the answer is, this is not so trivial, but it will be m minus 1 times n minus 1. So this will be our degrees of freedom. Let us now see, and you will see this will be a heuristic argument, as to why we will be using a chi-square random variable. We will consider quite simply a single cell of our table, and the argument will apply to every other cell of our table. Suppose we magnify now. We only consider one cell. Now suppose this is, if you look back, you ask, well, which cell is it? You have to specify in which row we are, and then in which column we are. So we need a row index and a column index. We will use I for the row position of our cell, and we will use J for the column position of our cell. So suppose that the cell is in row I and is in column J. Of our table. We will have two values in here. The first value will be the observed value. So after we sample our uppercase N subjects, each cell will contain a given value, an observed value. We will call this O for observed, and we'll write OIJ because it is in row I, column J, and the row index will always be the first index. So we will write OIJ. That is our observed value from our sample. The question is, under H0, under the assumption that the variables are independent, what should be the expected value of this cell? And we will call this EIJ, E for expected. So the expected value of the cell in row I, column J. Let's see how we can arrive at a formula for EIJ. Let me write this here very simply. So OIJ is the observed value in row I, column J. So I'll simply write the observed value in cell IJ. The first index always is the row position. And EIJ is the expected value in cell IJ under the assumption of H0. So let's see how we can find EIJ. Keep in mind, H0 is the assumption that the variables are independent. What we need is the row total and the column total of cell IJ. So I will simply write R, uppercase RI, for the row total of the ith row. So suppose that you say R2, this would mean add all the values in every cell of row 2, and that gives you the row total, row 2, R2. And Cj will be the column total. So for example, here if we said C1, we would add every value in column 1. The total is what we call C1. Well, since we are in row I, column J, the column total is Cj. And keep in mind we have in total n values. Uppercase N is our sample size. Okay, so now think of it. We are asking what is the expected value in row I, column J. If you think of it, this should be the probability to be in this cell times the total sample size. Well, if you think of it, the probability for a value to be in this cell is the probability it is in row I and in column J. So probability of, I'll simply write row I and intersection column J. That is the probability of a value to be observed in this cell. Of course, we want the expected value, and so it's the probability times the entire sample size. And here's where it's interesting. We are under the assumption of H naught, that the variables are independent. And if you remember, under independence, the probability of an event and the other is the product of the individual probabilities. So if we say that A and B are independent, and we say P of A and B, it's just P of A times P of B. So this will be quite simply the probability to be in row I times the probability to be in column J times the sample size. Well, if you ask what is the probability to be in row I? Well, how many values are in row I are I over, of course, the total number of values. If you have your row total over the total sample size, what you have is the probability that a value is in the ith row times, well, the probability to be in the jth column. Well, if you think of it, if you add every value in the jth column, you divide by the total number of values, you have the probability that a value is found in column J, finally, times n. We can simplify by dividing n over n, canceling, and we're left with something quite simple for the expected value in row I, column J. It is the row total times the column total over the sample size. So row I, Cj, over the total sample size. The question is now, we have an observed value in each cell from our sample, and we will have an expected value from each cell from this formula. The row total times the column total over the total sample size. The question is, how do we then use these expected values to come up with a statistic? The following argument will be a heuristic argument, just to give you a feeling for why the statistic makes sense. So let's go back to our single cell, and the argument will apply to every other cell of our table. So if I give you the cell in row I, column J, so we have the observed value, OIJ, and under H naught, the assumption of independence, we have the expected value, EIJ. Now if you think of it, think of observing each cell as you gradually sample more and more people. So you look in this cell, and you ask people for their favorite color, and then you enter a value depending on whether they're male or female, and their choice of favorite color. So gradually over time, the number in the cell will get bigger and bigger and bigger. And you stop when you decide that you have a large enough sample. Well, think of what this experiment resembles. So you start at time 0, you sample people, and every time that you have someone falling inside of this cell, you add +1, and in the end you stop whenever you have a large enough sample. What you're really doing is over time, you are observing the number of occurrences in this cell, and this is exactly the setup of a Poisson experiment, right? A Poisson experiment is, over a fixed amount of time, you look for the number of occurrences of an event, and this is exactly what we have. Imagine that you are sampling people over a fixed amount of time, and then gradually, every time you observe one person in this cell, you add +1. And in the end, you get the total number of people that end up in this cell, and that is the total number of of observation of a given occurrence over time. And so we see that OIJ follows approximately, this is again a heuristic argument, but a Poisson distribution. And what is the mean, right? The Poisson only needs one parameter, that is the mean, but the mean is the expected value. So under H0, OIJ will follow approximately a Poisson distribution with a mean and expected value of EIJ. If you remember, this is what we call lambda, which is the mean of the distribution. What was nice about the Poisson distribution was that its variance was also lambda. Therefore, the standard deviation is the root of lambda, which is the root of the expected value EIJ. Now the question is, well, what do we do with this Poisson distribution? Well, from the Excel assignment, when you constructed the graph of the distribution for a Poisson experiment, you must have noticed that the Poisson resembled a lot the normal distribution. That actually is the case. A Poisson is also approximately a normal distribution. And so the mean is EIJ. And the standard deviation is the root of EIJ. And now we're good to go, because if you think of it, our observed value follows approximately a normal distribution, and we have the mean and the deviation from the assumption of H0. We can now standardize and construct approximately a standard normal random variable for each cell. Right? If we standardize, we will get that the observed value, we subtract the mean, so minus EIJ, and we divide by the deviation, the root of EIJ. This will be approximately Z, the standard normal distribution. So if we square this, we will get approximately a standard normal random variable squared. And you may ask, well, why am I squaring? You'll see in a second. So if you square this, so OIJ minus EIJ over the root of EIJ squared, this is approximately Z squared. And so you see that under H0, we will have such a value for each cell of our table. We will have the observed value from our sample, find the expected value from the assumption of H0, and then compute this for every cell of our table. The next step is to say, well, what if we add all of these values for each cell of our table? What kind of random variable do we have? And we'll use the following notation. I use sigma for sum, which means adding up, and we have to add those up for every cell of our table. So we have to add those up for every row of our table and every column. So I will write simply I, comma j. And all this means is sum over every possible row and column of your table, so sum over every cell of your table. And we're going to sum this. I will simplify a little bit though. Right? If you square the top, you get O minus E squared. Over, if you square the square root, it just goes away and you're left with EIJ. Another question is, well, what is this approximately? Well, think of it. For every cell, we roughly have a standard normal random variable squared. Now we're adding these variables. And if you remember, this is exactly the definition of a chi-square random variable. It is a sum of standard normal random variables squared. So this will be approximately a chi-squared random variable. The only question at this point is, what are the degrees of freedom? And as we have said before, it will be the number of rows minus 1 of our table times the number of columns minus 1 of our table. And so we now have our statistic. There is only one question left, and that is, how do we know if this supports H0 or goes against it? Well, let's think of it. Let's go back here. We will have for each cell an observed value, and under the assumption of H0, an expected value. So if H0 really is true, the value observed should be really close to the expected value, because what this says is, if you really had independence, this is the value that you should have obtained in this cell. This is the one that you have obtained. So on average, if you truly have independence, O and E should be really close to each other. So let's write this down. So if H0 is true, because H0 is the assumption of independence, so if H0 is true, we would expect our observed value for each cell to be really close to the predicted value under H0. But now think of it. If O is really close to E, that means the difference will be very small. So it's about 0, so it's very small. So if you square it, it won't be too big, and if you divide by E, it will also get smaller. And so it means that if H0 really is true, these terms must be fairly small. And of course, if you're adding small terms, the result should not be too big. And so our observed value of chi-squared should be fairly small. That's the idea. So a small value of chi-squared, and if you think of it, you're summing squares. So the only way for the whole sum to be small is if on average the terms are pretty small, and the only way for this to be small is if this is a rather small number, therefore O is very close to E. But if O is very close to E, this says that the observed values are really close to the expected ones under the assumption of independence. This supports H0. And this is our conclusion. So if chi-squared, our observed value, is small, then our conclusion is to accept H0. Because the only way for this to be small is if O is very close to E on average, which does support H0, the assumption of independence. The other hand is if chi-square is too big, well, if this sum is very big, the terms must be on average big, and the only way for this to be big is if O minus E is big, therefore there is a big difference between the observed value and the ones predicted under independence. Therefore this would be evidence, so a large chi-squared value would be evidence against H0, and so we would reject H0. So if you think of it, we will accept H0 if chi-squared observed is small enough, reject H0 if chi-squared observed is too large. So we are rejecting large values, and so in the case of a test of independence, we will always have a right tail test. We will always reject the right tail of our chi-square distribution because the right tail contains large values, and large values are evidence against H0. So always keep this in mind. And you see, heuristically, it's very intuitive. You think, okay, I find for every cell the expected value, I compute this and I add this up for every cell. I have my chi-squared random variable with this degrees of freedom. If chi-squared is very small, that means that O is very close to E, which supports H naught because E is the predicted value under independence. But if chi-squared is large, then O must be far from E. But again, E is the predicted value under independence, which means that what we should get from independence is really not the case. And so this points towards dependence, therefore against H naught. And so large values are evidence against H naught. And that's why we will always reject the larger values of our distribution, therefore the right tail. And so we always have a right tail test. In our next video, we will see an example of such a test of independence.